Good day, welcome to part 2. We're looking at lattices. Lattices are going to be an interlocking pattern of atoms, and we're usually talking about solids when we're talking about lattices. But of course, let's talk a little bit before we talk about lattices, and let's talk about what solids are, and of course, liquids and gases. Okay, elements and compounds and really stuff around us can come in different phases. The three that we usually see the most often are going to be solids, liquids, and gases. And we can denote on our chemical by doing a parentheses, S parentheses, parentheses L parentheses, or parentheses G parentheses to denote which one it happens to be at that time. Now, solids, they're going to have fixed volume and shape. Of course, you probably already knew that. Their atoms are going to be close to each other, and they generally don't move past each other. Liquids, fixed volume, intermediate shape. Their atoms are close to each other, and they do tend to move past each other. Gases, on the other hand, they're far apart. They move past each other like crazy. These are not the only three phases you got. We, of course, have plasmas, which are a lot like a gas, but the electrons have bounced off because it's so ridiculously hot. We have supercritical fluids, which is kind of like a gas and a liquid at the same time, as well as you also talk about things like plastics, liquid crystals, and a few other kind of weird phases that we will mention briefly. Now, let's talk about lattices. Solids can come in a couple of different flavors. Usually we think of them as crystalline structures, what we call a lattice, but they can be amorphous. If it's an amorphous, the atoms are just in the old place, or the molecules, depending on which one this thing is. But in a lattice, you get this nice repeating 2- or 3-dimensional pattern of whatever building blocks your solid is made out of, either atoms or molecules, probably. This repeating structure, the actual 3D pattern, is known as a lattice. Now, it may or may not be perfect. You could have cracks in it, like we have over here. These cracks in the lattice play an important role for things such as metals, where they will change the ability of the metal to bend and flex and not fall apart. Not something we're going to inherently jump into it. Your lattice could be nice and orderly. It can come a couple of different shapes. It can be more of kind of the cannonball stacking or more of just kind of a grid pattern, depending on what you have. As well as you can have impurities. You can have simply just not having a thing there. You can have a vacancy. You can have an impurity that's basically the same size. You can have an impurity that's a whole lot bigger. You can have a couple of different flavors for your lattices. Now, I should also point out that you do have things like liquid crystals and plastics, which have generally some level of lattice structure, even though they're not really even a solid. They're this intermediate phase between solids and liquid phases. They do generally have some 3-dimensional structure, but it's somewhat more in flux. That's actually about all we're going to deal with those for this course. Those are usually handled more in engineering courses because the engineers get to really deal with those things. Now, we've got a bunch of atoms. We need to hook them together to form the lattice or the molecule or whatever we're dealing with. And there's 4 main ways to do this. They're all going to be based on opposing electrical charges. Opposites attract. Positive is attracted to negative. First choice we've got is an ionic, quote, bond. A bond implies sharing of electrons. In this case, they're not exactly sharing. If you have cations, remember from Unit 3, cations are going to be an atom that is short an electron. Well, if it's short an electron, it's going to be positively charged. Anions are an atom that is plus an electron. It's got an extra electron, or 2, or 3, or more. Well, opposites attract, so those two are going to want to interact with each other, and they will basically, static electricity, cling to each other. If you get a bunch of cations and a bunch of anions, they'll tend to arrange themselves in some kind of grid. A lattice. This is what we call ionic bonds, even though bond is a little bit misleading here. Metallic bonds, in that case you get a bunch of generally metal ions. They're going to share some of their electrons all together, kind of a nice little electron commune, and create what we know as an electron sea. Covalent bonds, not so much more individual. 2 atoms are sharing a pair of electrons between each other, not between all their neighbors, just between each other, and it's a nice sharing relationship. We also have intermolecular forces. These are a cousin to the ionic bonds, but it's not really that someone lost an electron. It just happens to be the electrons are on one side of the molecule for whatever reason, and thus you have a slightly positive or slightly negative charge. Quite often, a lot of these things are going to be going on at the same time. It is not an either-or scenario. It is quite often talked about as either-or, but it's definitely not. You can have very unequal sharings and other more complicated stories. Now let's talk at bonding preferences. Generally speaking, metals and nonmetals, when they bond, tend to form ionic bonds. Once again, they could be sharing, just doing a really bad job of it. Remember, metals tend to be less electronegative. They don't really want to hold on to their electrons as tightly. So it's very easy for them to become cations. Anions would love to gain an extra electron. They hold on to theirs very tightly. So it's easy for them to become anions. So non-metal, metal, very good chance that's going to be an ionic interaction. Now, there are certain cases, such as like magnesium chloride, where it's ionic, but they're also sharing that electron. So it's a much more complicated story here. Now, metals with just metals, so a metal and a metal, those are probably going to prefer to form a metallic bond, which is kind of intuitive from the name. They don't really want to hold on to their electrons quite so tightly, so they're kind of willing to let the electrons kind of share between the whole group. No one's really trying to grab the electrons, no one's really trying to keep their own, that kind of scenario. When two nonmetals bind, they're more than likely going to go for the covalent route. They both want the electrons, so they'll share. They're not going to be able to steal it from the other one, so they'll share. Now, once again, how evenly they share, that's a whole other story. And we're going to get to that in Unit 5. Because some people are better at sharing than others, and some atoms are better at sharing than others. So let's look at the ionic bonds. As I mentioned, they tend to form some kind of grid pattern, the lattice. This is when they are solids. Ionic compounds can be liquids. There are even room temperature ionic compounds. Cutting edge research on that one. They're not dreadfully common. Most ionic compounds are going to form that lattice, and they want to stick to there until it gets ridiculously hot. So a lot of these things are very high melting points. So you're going to get yourself with a bunch of cations, a bunch of anions. They're going to interlock themselves in some form of grid. Now, quite often, you see this kind of cubic grid, which we see in sodium chloride. That's over here. There are a ton of different configurations for them to go. You'll notice this is not that. Depending on the size of the atoms, the charges on the cations and the anions, different preferences for the way they stack. In chemistry, we're not going to go too deep into the way they stack. That's really important for the geologists as well as the engineers. It is becoming more important for chemistry. It's still the emerging area. Now, metallic bonds, basically you're going to get yourself a nice lattice again, but many of your atoms are going to let their electrons run free, what we call delocalized. They're going to be able to travel readily across the material. This allows metals with nice metallic bonds to be good conductors of heat and electricity. Obviously, if the lattice gets broken apart in imperfections, what we call grains, then your conductivity may have issues. That's one of the issues with aluminum wiring for houses. It can get issues with its grain structure and thus hot spots. And you don't really want hot spots in your wiring. Because all these guys are positively charged or neutrally charged, they're generally able to slip past each other. If you caught the previous slide, you'll notice that when an ionic compound is trying to slip past each other, all of a sudden you're going to go cation, you disrupt the lattice, and ping, it breaks apart. Ionic compounds are generally very brittle, whereas metallic compounds, or alloys, depending on how you want to think of it, which are mixtures, tend to be much more ductile, much more malleable, because you've got cations sliding against cations all in electron C. You don't have any scenario where if you disrupt the lattice, the whole thing falls apart. Now, covalent bonds, those are going to be the sharing of two discrete electrons. Now, those two electrons are shared between two atoms, generally speaking. There are scenarios where they are shared between multiple atoms. We'll talk more about that later on. But generally speaking, it's two electrons shared between two atoms. If there's multiple sharing relationships, like is going on in that methane molecule on the bottom right-hand side, that carbon is sharing two electrons with the hydrogen on its left, and two different electrons with the hydrogen on its right, two different electrons with the hydrogen on the top, and another 2 different electrons with hydrogen on the bottom. They're sharing them. The electrons are hanging out around carbon and around hydrogen, but it's a very discrete case. These things aren't going to want to slide past each other. They are physically hooked to each other, well, electrically hooked to each other. So generally speaking, covalent bonds will rotate, they'll spin, but they don't shuffle around much. When you have covalent solids, this is where you have a couple of different scenarios going on. You can have network solids, which are very much like the ionic and metallic solids, just in this case, instead of having a sea of electrons or having positive and negative charges, you have discrete sharing arrangements in a grid-like pattern. They tend to be fairly brittle. Things like diamond and glass, both of which are actually fairly brittle, fairly hard as well. They don't want to change shapes at all. However, covalent molecules can also form, or covalent compounds can also form molecules, which are small, discrete clumps of atoms. And then those molecules might happen to stick to each other using intermolecular forces. And intermolecular forces are generally much weaker. In those cases, your properties of your solid are heavily dependent on how the molecules are interacting. You're not breaking any chemical bonds when you're trying to break them apart because you're simply taking a molecule out of it. These are known as molecular solids once again. We'll talk more about those here in a little bit. Well, that wraps up that part. We're going to jump for one more part of salts and lattices and then on to Unit 5.